Thank you, Holger, for your introduction. So, good afternoon, everyone. My name is Guoliang. I'm from Technical University of Darmstadt, and my presentation today is about curvature approximation for the unstructured geometric VOF method. This is a group work with my university colleagues and also colleagues from Robert Bosch company. So the agenda is basically 4 parts. So it's still a preliminary study. So the content may be simplified to you. So first is the introduction part. I'll give a brief introduction on VOF method. So our solution domain omega is split into subdomains omega minus and omega plus. So omega is separated by the fluid interface sigma t, and tau t is the interface connect with the wall, and it has a contact line and a contact angle. So the fluid phase omega are indicated with a phase indicator chi as 1 in one phase and 0 in another. So with the VOF method, we can have a single field 2-phase Navier-Stokes equations. So the constant phase specific density rho minus rho plus and the viscosities mu minus mu plus are modeled using the indicator function, and we have the phases are well assumed to be incompressible. So we have the continuity equation, and the momentum conservation is this. So here the F sigma is the surface tension force, and we use CSF model to model this force. So for CSF model, it's like F sigma equals to sigma kappa and the gradient of alpha. So I think it's familiar to you if you know VOF and the CSF very well. So alpha here is the volume fraction of a fixed control volume omega, and yeah, here is how we calculate alpha in a cell, and we rely on unstructured finite volume differential operator for equation discretization because we're using OpenFOAM. Yeah, it's a finite volume method. So and the curvature approximation is like the kappa is equal to the minus the divergence of the NC is the interface normal vectors. Yeah, so cell-centered interface normal vectors. So there are some challenges regarding this curvature calculation. First is that the divergence operator here is a volumetric operator because we use a volume finite volume method, but yeah, and requires the interface normals to be defined outside the interface sigma. Well, by definition, the interface normals should only only available on the interface. That's one, and the other challenge is that the interface normals outside the interface omega may vary in normal directions of the surface. So because it's like live not only on the surface but also some point away from the surface. But the interface normal by definition should so it's only a surface, so it should only vary along the tangential direction of the surface. So that's 2 challenges where we want to employ this equation on a finite volume differential operator. So how to solve these challenges? There are actually already a curvature model called RDF curvature model that's already made some effort on this. So this is a curvature model from 2-phase flow. It's a geometrical VOF library that's open source available. You can it's based on OpenFOAM. So how does it solve it? So first, it compute the reconstructed distance function called RDF. In interfacial cells are the cell contain the interface where their alpha value is between 0 and 1. So it's compute RDF in interfacial cells and 3 layers of point neighbor cells using plaque. Yeah, they use plaque to reconstruct the interface inside the interfacial cells. So they calculate RDF in these cells, and then they take the gradient of the RDF field to get interfacial cells and two layers of point neighbor cells. The cell-centered interfacial normal vectors, unit normal vectors. And then with these normal vectors, they can then compute the curvature from the divergence of the unit normal vectors. Or rather, they choose another way to use the trace of the gradient of the unit normal vectors. So these two are mathematically equivalent, but with using a gradient scheme, they can use a numerically high order gradient scheme to improve the accuracy of the curvature computation. So now we have the cell-centered curvature values, but actually we want the curvature value on the plate, on the surface, on the interface. So next they do just an interpolation to interpolate the cell-centered curvature to the plate center. Then that's how they like doing this, but several drawbacks. So first, they construct our RDF across cells. You see they cross like 3 layers. So they are using a class called index octree in OpenFOAM. And this is like computational expensive, especially in parallel computing. And another drawback is that they still have like artificial gradient along the normal direction because they only use like the nearest point to compute the RDF. So the point may not lie on the interface normal vectors. This is particularly a problem when you have like cells away from the interface. So now come to our work. So we propose an algorithm, like to summarize it with one sentence, it is to extrapolate the interface normal. We call it the div normal, and I will give you the details. First, we also need the plaques information to calculate RDF, but we calculate in a different way. So we calculate using a averaged sum. So these are the cells that contain a plate surface and plate normal and plate center. So in these cells and the first layer of their neighbor cells, we use this equation to calculate the RDF. So for this cell, we use this cell and all its neighbors that contain a plate surface to do a averaged sum. And we choose the weight as using this weighting equation. And here is that we use alpha times 1 minus alpha to filter out the wisps. Wisps are the cells that contain a very small or contain their alpha value is very close to 0 or very close to 1. So their surface in the cell will be very small. And this is actually a reference from this paper. I think this should be the original paper to calculate the curvature using RDF. Yeah, we only calculate our RDF in the interfacial cells and its first layer neighbors. So rather than like the previous one, they calculate for 3 layers. We don't need the index octree, only layer by layer. And then we propose a interpolation scheme. It's called IDEC. IDEC is the short for iterative defect correction. It's a reference from this GCP paper. And it's basically like it's a iterative method. So you see, we're using the interpolation scheme as this. So we have the green point here, and we have values at cell centers. So we use these cells, point neighbor cells, to construct the interpolation stencil, and we propose this interpolation scheme. So K is iterations. So you can see that if K equals to 0, This is basically inverse distance weighting because we use this inverse distance as a weighting. But when k is larger than 0, when k becomes 1, 2, and within each iteration, we manage to find its first order defect correction, defect term, and then we get rid of this term. So it's called defect correction. And yeah, the iterative process stops when phi k plus 1 minus phi k is smaller than the user-defined value, or the iteration reaches maximum. So it can be proved that if the gradient term is determined at least to first order accuracy, then this interpolation scheme can have a second order accuracy. So yeah, with the RDF we computed earlier, we take the gradient of it and we have the interfacial self-centered unit normal vectors live on the interfacial cells. Then we use the ADAC we propose and to propagate it to the first layer of the point neighbors. But here we need to carefully choose because we don't want any normal artificial gradient in the normal directions. So usually when we are doing inverse distance weighting, we like use the red lines as their distance or over 1 as the one over this distance as weighting. But imagine if this point is exactly on this blue line, so the normal vector on this point should be exactly as this one. Yes, so we don't want any variations along the normal direction, so we get rid of this the weight that come from the normal direction, the blue one. Yes, we use the red one minus the blue one as the final interpolation scheme, the green one. So, and using this method, we propagated the interfacial cell normals to its first layer neighbors, and then we have enough information to calculate the curvature at the interfacial cells. Just use this equations. And yeah, now we have the self-centered curvature at interfacial cells. Now it's also the problem how to calculate the plate-centered curvatures. So here because we'll assume the interface is locally spherical and the self-centered curvature can be correct. We can only use a correction weight to the plate-centered because we have the sign distance information, the RDF. So this is reference from this paper. And you can say that it's a compromise between accuracy and efficiency because we can also like use interpolation, but interpolation needs its neighbor information. But if we use this correction, we will only need the cell local information. So that's all for the algorithm, and we have some verification case. So my presentation is mainly focused on curvature approximation. So we have this computational domain as a cube, and we have we have two geometries. First a sphere, and second is an ellipsoid, all located at the center of the box. And the mesh we have is a hexahedral generated by a block mesh, and the grid space is from 20 to 200 cells uniformly distributed along each x. And we use the reconstruction scheme as we use a plate RDF. So I don't know if any of you like using this. It's the ESO vector invented by Johan. I think he should also like attend this workshop. And we compare our normal curvature model with the RDF one that I mentioned before. RDF curvature model, not the not the sign distance, but the curvature model. Yeah. And we have some error definition. So we compare the interfacial normals because we calculate the curvature from the normals. So we define the L1, L2, and the L infinity normals. And for sphere, the normals is like easy to calculate. You only need the cell center, the cell center's position vector and the sphere center. But for ellipsoid, it's a little bit difficult. So you need to find the interface normal vector of the ellipsoid that pass through xi. So that's for normals. And for curvatures, we have two kinds of curvature. First is the cell-centered curvature. Cell-centered curvature for sphere is also very easy. Also, we only need the cell-centered position and the sphere center. So the mean curvature is evaluated here. And for ellipsoid, we use the trace of the gradient of the exact interface vectors as the exact curvature for error evaluation. And for plate center, it's rather easy. For sphere, it's just 2 over the radius, and for ellipsoid, it's quite a. If you have seen the curvature for ellipsoid, it's quite a long formulation, but you can refer to here. And yeah, for sphere normals, you can see the red lines are RDF and blue lines are our methods. So this is the interfacial cell-centered normal, and it's the first layer propagated normals are all better than RDF. And this is for curvature. Again, R is better. And for ellipsoid, yeah. And for ellipsoids, curvature still so better compared to RDF. Yeah, conclusion. So still, yeah, like I said before, it's the preliminary work and still a lot of things to do, but we managed to construct a second order interpretation scheme, and we propose this div normal algorithm, and we verified compared to RDF is only for curvature approximation is better than RDF. So thank you for your listening, and also some questions. Height function. Actually, in two-phase flow, they have a curvature model using a height function, but yeah, it only can works on hexahedral mesh. Yeah, height function is something like this. So if you see the sphere curvature, it can converge to like first order. Yeah. But I'm only talking about the height function in two-phase flow library. So as I found out that they are very sensitive to the initialize of the alpha field. Yeah, you have to initialize your alpha field using a very accurate method. You know, if you initialize the alpha field using set alpha field, then the height function is crap. Yeah.
Thank you, Holger. So hello, everyone. Today, I would like to present our joint work, which is performed at Montana Universität Leoben in Austria. So we are Christian Doppler laboratory. It means we are combining the cooperation with industry. So these are RHI Magnesita, who produces the refractories, and Primetals, which actually build the continuous casting machines. And I would like also to thank my former colleague and my friend from Czech Republic. So he assists with assessing the models for conjugated heat transfer and cooling systems in continuous casting. So I would like to start with introduction. For those of you who don't know what is the continuous casting process is, this is long line from the hot melt prepared with converters or different furnaces, which is then poured to the continuous casting mold, and where the first solidification occurs due to the cooling of the copper mold. So such products, you can imagine, they can be used in the car industry for rolling. So these are called the slab products. Okay, so we will focus on the mold region. So we have highly turbulent flow, solidification, and corresponding cooling and behavior of the free surface. So generally, the continuous casting is a combination of multi-phase phenomena. So it's turbulent flow, solidification, then free surface. Then it can be different particle or gas bubbles motion. And of course, to increase quality, the question arises, how can we control such a process? And it can be controlled by so-called electromagnetic braking. So here in reddish colors, you see the area of application of transversal magnetic field. So there are special devices which are producing the magnetic field, which is normal to this mid-plane of the domain, which I show. And interesting thing that, due to the Maxwell laws, Maxwell equations, we get some induced electric current since the metal is contains electrons. So this is like the motion of electrons in the magnetic field, which induces this electric current. And you can see, so if we consider this as an isothermal case, we have very strong fluctuations. This is like pumping energy in the system, and it destabilizes the flow. But actually, we intend to control it. So that's why we should really consider the presence of the conductive solid shell. So when the metal solidifies, also the conductivity increases. And you can also see that the induced current lines, they start to close through the solid shell. And we have mixed effect. So we have some braking effect, and we have still have some mixing and fluctuation, which is desired for solidification. And the level of this effect can be defined by so-called conductions ratio. So this is the conductivity of the liquid bulk and conductivity of the solid shell. So the stronger this conduction ratio is, the stronger you are breaking the turbulent flow. Yeah, so this is generally how the effect works in the real casting. So you have some oscillative flow with here with the superheat distribution on the left. So then when we apply some mild magnetic field, it starts to break, and we keep more superheat at the top. And here, with very strong magnetic field, you can even see some stagnation zones. And so you should apply this process to some limits, because actually, during our studies, preliminary to the study which I present today, we have found, which is also approved by experiments, that with growing magnetic field, you can actually start reversing your flow, because the application of electromagnetic braking, this is actually a redistribution of the linear momentum. So you are not braking everywhere. So you can brake in some area and accelerate the flow actually in different zones. So yeah, you can see there is a classical flow pattern in such system. Then you start generate some small reverse zones, and then the reverse zone can even dominate the upper part of the mold. Yeah. Also, this is how the turbulent jet behaves under transversal magnetic field. You can see that it starts to extend along the magnetic field lines, and actually there are different reverse zones appearing above and below this jet. So which was actually predicted in Davidson in his book Magnetohydrodynamics. And so recently we performed the studies which in details also repeat this effect. Okay, but let's come to the motivation of the current study. So it's bluish because this is from industry, so I just don't reveal the details. Actually, there is nothing, but it's just for, so they have a sequence of electromagnetic braking power, and they measured the wave height and submeniscus velocity. So we assessed also some complex model, including like cooling in the mold, presence of the insulating liquid slag, which actually stops. So it stops heat flux and induced electric current. So you see that our induced current lines remain inside the liquid bulk, so they don't go to the copper mold. And so we tried to compare our measurements, which are actually based on single phase modeling. So you can use some kind of Bernoulli approximations to estimate the wave height. And so we got really big difference. So at least we were same order on the submeniscus velocities. So this, I think this is, yeah, the orange lines, but we underpredicted the wave height by like 2 or 3 times. So that's why I changed, decided to perform such simulations using WOF. And actually initial simulations comparing the Euler's for WOF implementation with IZ vector from Johan Rönnby. So it showed that we get in our domain a huge amount of these spurious bubbles if we use this algebraic Euler's. And yeah, we get almost none of them if we apply the IZ vector. So this gave us motivation to go more in this study. So, and just briefly to explain you how the magnetohydrodynamics can be included in the turbulent flow. So we have the incompressible Navier-Stokes, and so just briefly saying we use large eddy simulations. So this wall adaptive large eddy, because it also includes not only the gradient of velocity, it also includes the helical component, so the second invariant of gradient, since the turbulence becomes quasi 2D under the applied magnetic field. Also, yeah, I heard during this conference the sigma model, so I will give a try and see how it relates to the experiments. So to close this system, we need to calculate the Lorentz force, which is calculated from equation 3, and induced electric currents J, they are calculated from Ampere's law. But it's very hard to apply some boundary conditions for the total magnetic field by also, and those of you know the MHD, so the induction equation, so this is really a pain. So, but in continuous casting, we have a low Reynolds magnetic number, and we can reduce our problem to constant magnetic field. That's why our electric field E becomes curless, and we can substitute according to the vector field theory. We can substitute it with gradient of potential function, which is called electric potential. So we transform our equation into equation 4 by integrating left and right side, transform to a Poisson equation for the electric potential, and we close with corresponding boundary conditions. So I don't go into details, you can ask later. Yeah, and also numerically for OpenFOAM, we applied here the surface reconstruction of induced electric currents and surface reconstruction of the Lorentz force, because this gives you a conservative formulation of these forces and induced electric currents, which are not accessible if you calculate everything in the centroids of the finite volumes. Yeah, so we verified single phase model with the experiments, so it gave corresponding. So good agreement, but let's switch to the two-phase modeling. So we used the same benchmark as in the single phase. So this is well-known Galenstam experiment in the Dresden, but here now we included the free surface modeling under applied magnetic field. And what was important, so what we found very important for the VOF modeling, since we calculate so this fluxes everywhere in the domain, it consists of non-conductive phase and very conductive phase. It is very important to properly interpolate on the interface. So you can imagine, so if we apply the linear interpolation between the non-conductive phase and very conductive phase on the right. Even with like 10% of conductive phase, you get very strong conduction in this area. And our model doesn't feel interface and can penetrate through the interface into the non-conductive liquid. And it also doesn't really feel the bubbles which are entrapped in the system. So we applied, so actually both of them can be applied, but harmonic is more, we applied geometric and harmonic interpolations. Harmonic is more tough numerically. So here you need apply some under relaxation. But what we achieved, we really stopped the induced electric current and the interface of the non-conductive liquid. It is especially important if you entrap some non-conductive gas bubbles. So you see, we don't have induced electric current inside the bubbles. Yeah. So coming to the main topic, so comparison of the models. So what I will compare, I compare the algebraic Mulus and geometric plic and mplic from the OpenFOAM 8, from foundation version. Then I use IZ vector from easy version 2012. Also, in the benchmark, I didn't use the large eddy simulations. For simplicity, I used K omega model. And I use linear gradient scheme for the velocity, and for K and omega, I use cell limited. So this provides a physical bounding of the K and omega, doesn't allow any to go to the negative values or overshoot. And yeah, so linear upwind for the momentum term, advective term, and also linear upwind for the turbulent variables. Yeah, so I just took standard settings for Mulus. It was interface compression Van Leer, standard for plic, interface compression Van Leer, and mplic scheme. Yeah. And so additional, there was IZ vector scheme. So actually what we are speaking about is how to solve this advection equation for the volume of fluid. Yeah, so these are just descriptions from the homepage. You can find the more details about these models. And I used the IZ vector from Johan Rönnby for the comparison. So I simplified benchmark because the Dresden experiment, it was like 10 million cells. So I reduced the domain to half size. So you see we have the feeding jet from the left side, and there is some outflow here. And in the case of application of the magnetic field, so MHD case, we'll have the uniform in the whole domain, uniform magnetic field applied transversal to the jet. So first I compared just non-MBR case without magnetic field. And so here I scaled the volume of fluid to 95%, so that we can see some small bubbles which actually come from the numerical diffusion of. So these are parasitic bubbles from the numerical schemes implementation. So we see that plic and mplic still contain a lot of these small bubbles. And then, so yeah, if we change to the IZ vector, so actually I have to check. So this the residual bubbles, do they still come from the numerical scheme, or these are really entrapped? And so then when we apply the magnetic field, so now you see the declining of the jet. So actually, to my schematics, it is mirrored the results. So jet is going from right to left, because then we see entrapped bubbles more clearly. So I took a special moment. So all schemes were using the same time stepping, so that we can compare at some stages when the bubbles are entrapped, how they behave. So this is for Mulus. and for the plic and mplic. So we see that quite big bubbles are entrapped. And in the case of the IZ vector, so we have many small bubbles entrapped into the domain, because you can see that there is a strong reverse flow which applies very strong shear rate on the free surface here. Yeah. So and then so I compared actually what is the final stage. So I ran for 20 physical seconds, so it's already like several times, several characteristic times to fill up this domain and change liquid in the simulated domain. So we see that, yeah, there are many bubbles, so really entrapped or coming from, we see that there are really some small bubbles following the advection direction. So this comes from scheme. So we have here some very quite big bubbles entrapped in this circulation zone. The trend is reduced in case of plic and implic, but we still entrap here very big bubbles in the zone. And yeah, so we don't see so much bubbles coming from entrapment and numerics in the IZ vector scheme. So we are in this initial stage of this analysis, and but what is good, we see that our MHD model correctly treats the bubble, so we have induced electric current going around this non-conductive phase. And so coming to the conclusions, so you can find step by step these studies, which all of them are performed in OpenFOAM, also with a description of numerics, which we applied in consequent publications. So the last one was on this VOF modeling for the Guoliang experiment in Dresden Center. And so we would like to finalize this work and make consistent study and present it as an OpenFOAM journal publication. So with that, I would like to thank you for attention, and I'm open for your questions, please.
Very nice.
Yeah.
Okay.
Yes, again. Yeah, so on this benchmark, so this benchmark was around like 300,000 cells. So I didn't really feel the difference between the schemes. Yeah, of course it should be different. Yeah, you just solving the algebraic or you reconstruct. Yeah, so I will perform it on bigger mesh with bigger, higher resolution, and there the difference will be more noticeable. Yeah, but I didn't see big differences. Yeah. Mm-hmm. Okay. Yeah. Thank you for your question. So it's so I should repeat. Yeah, the question. So what is the time estimation for these benchmarks, and what are the calculation resources? So this benchmark which I present, it runs on single CPU, so just Intel around, I think 3000, so 3 gigahertz. It runs within 1 day, and in parallel, so that benchmark will be like 8 times bigger. So let me see. Yeah. So it's not really. So on HPC, I will run on similar but 28 cores. So, and it's reasonable time, like a couple of days of simulation.
Hello, everybody. Thank you to see you in such a large number. I don't know if it's the interesting presentations or the nice, cool room. But anyways, my name is Fran. I am a PhD student at the Department of Physics, University of Cambridge. And today I'll be presenting my PhD work titled Numerical Modeling of Cavitation Erosion using a polydisperse fluid formulation, which I did under the supervision of Dr. Yasak and my industrial partners from Afton Chemical, Walid Al-Salami, and William Anderson. So in this presentation, I'll briefly go over cavitation erosion, cavitation erosion, and computational cavitation erosion. I'll speak about the motivation of separating the problem into a bulk fluid model and a cavitation erosion model. And lastly, I'll give a brief discussion and conclusion. So all fluids, engineering fluids, have nuclei present in them in the order of 10 to the 7 per meter cubed for ocean water. As these nuclei experience pressure changes, they grow and potentially collapse. If that happens near a surface, they may induce surface erosion. If we look at experiments and numerical data, we can see that the magnitude and occurrence of cavitation erosion depends on the number of bubble collapses, the bubble collapse driving pressure, and the bubble standoff distance, which is the ratio of the bubble diameter and the distance of the bubble from the surface. We discern between two bubble collapses: symmetric bubble collapses, which happen in a uniform field, which is usually far away from the surface, and non-symmetric bubble collapses. The figure, I can use my mouse too. The figure on the bottom left shows the, let's say, depth of bubble. So if you can imagine a rigid surface at the bottom, the bubble starts as a sphere. The top or further pole collapses inwards until it touches the bottom surface here. It emits a microjet in the order of hundreds of meters per second, which hits the bottom rigid surface with the pressure wave seen here. So this first spike. What we're left with is a toroidal structure or a donut-shaped structure, which also collapses and emits a second pressure wave seen here. If we look at the video, we can see how that looks like. So this is the initial microjet expulsion and the toroidal structure collapse and emitted pressure waves. Depending on the distance of the bubble from the surface, we can see different damage patterns. So the leftmost damage pattern is when the bubble is close to the surface at a distance of 1, so 1 diameter from the surface. The damage is centered around the microjet area, and going further backwards, it's spread due to the toroidal collapse. What are the main difficulties of computational cavitation erosion? Firstly, there are thousands of collapse events per second. Next, there is a wide range of both temporal and spatial scales. So bubble collapses occur in the order of 10 to the -5th, 6th of a second, while cavitation erosion damage takes minutes, hours, days, weeks. The spatial scales are also widely different. Bubbles are in the order of micrometers to millimeters, while engineering devices are in the order of centimeters, meters, tens of meters in case of ships. So the idea here is to separate the problem into two individual, let's say, problems. The first one is the bulk fluid model, which is supposed to provide a bubble collapse model with the 4 factors we're looking for. So the number of bubble collapses, the pressure, the bubble collapse pressure, and the bubble size and distance from the wall. So let's start with the bulk fluid model. Here, there are several modeling approaches that people have used. Ideally, we would like to use something like the Euler-Lagrange methods. However, it is extremely computationally expensive, especially if you look at something like 4-way coupling, and it's basically applicable to some validation cases or extremely simple geometries. Next is an interesting idea, which is called the hybrid Euler-Lagrange, in which larger structures such as cavitation sheets are represented in an Eulerian frame, and as they become smaller or detached, they are transformed into a Lagrangian frame, and vice versa. However, that is also expensive and perhaps maybe more applicable to cavitation sheets and larger structures like that. Lastly, there's Euler, which is computationally acceptable for cavitation erosion. In this category, we have monodisperse models or polydisperse models. The idea behind this PhD is to look for polydisperse models, as again, we're interested in the bubble diameter from the surface. We can describe this polydispersity by either solving a population balance equation or using a multifluid model in which we consider bubble classes to be fluids which interact with the continuous medium, which is water or lubricants in the case of this project. So we take our continuity equation, a phase fraction equation, and momentum equation. We volume average them and condition them using the VOF, and we get this set of equations. We need to close three terms to solve them. We need to figure out MI, which is the momentum exchange terms, RF effective, which is Reynolds stresses, and S phi, which are mass exchange terms. Starting out with momentum transfer, only two-way coupling is considered. So momentum is exchanged between bubbles and the continuous phase, but not between bubbles themselves. These are the terms or forces that we consider: drag, virtual mass, lift, turbulent dissipation, and the wall lubrication, which is a bit made up just so we keep the bubbles from the wall. And the real difficulty is in finding the values of these coefficients. Next, we have closures for Reynolds stresses. Again, we use the Boseninsky viscosity and the modified K epsilon turbulence model. You can use K omega also. The difficulty is how to model these bubble-induced turbulence terms. So I assembled my set of equations and I looked to validate them. I used two separate databases, LEU 1989 and LEU 1998. I didn't know a lot about closure models or what were the guidances, so I used my codes to compare what two different groups use. The first group is HDDR, and the second group is nuclear engineering from MIT. Most of the terms are quite similar. Virtual mass, most people agree it's constant at 0.5. Drag, Ishii-Zuber, or you can use Tomiyama. It's quite similar, and the only difference is terminal velocity and kind of a small portion of bubble-induced turbulence. Turbulent dissipation, you could use Antal, but more common recently is Burns. Lift is some variation of Tomiyama, in this case, Hessenkemper, and we try to model the aspect ratio using the Ziegenheim-Lucas model and treat the reduction of lift near the air with a Shaver-Podolsky correction, let's say. Where these two groups kind of differ is how they treat the forces near the wall. HZDR uses the Hosokawa wall lubrication model and the bubble-induced turbulence of Ma, while the MIT has their own developed models. This is the wall lubrication by Lubchenko and the bubble-induced turbulence by Guoliang. So starting off with the first database, dots are experiments. Red line is HDR, blue line is MIT. At the top, you have your continuous and dispersed velocities, and the bottom, your phase fractions and your kinetic energy, turbulent kinetic energy. So just briefly going through these slides, you can see that the blue line matches the results better, especially this curvature and the amount of turbulent kinetic energy. If you look at the next experiment from the same data set, you would probably agree that the blue line matches a bit better. If you use the same settings, let's say, or same coefficients on a different database from the same author, but 10 years later on, you can see that the results vary widely. So most would agree that the red line in this data set looks much better than the blue line. Looking at the next experiment from the same second data set, again, red results look much better than blue results, except for, again, turbulent kinetic energy. And looking at the last result of this data set, you can see that both results kind of look okay or bad, depending on what your criteria is. So this brings me to a brief conclusion of momentum interchange terms, is that there is no set guideline. It's very application based. It depends on your velocities, your phase fractions, and your application. So if you hope that I would give you a best guidelines practice, it's unfortunately, I don't know it myself. After modeling or validating momentum exchange terms, I looked at mass transfer. The framework is a sectional class method because we can use block-coupled solutions of the phase fraction equation, and we can use separate velocity fields for bubble classes, which we expect the bubble classes to vary widely in their size. The discontinuous terms such as coalescence or breakup are handled by the fixed pivot method of Kumar-Ramkrishna, and the continuous terms such as cavitation is handled by a mass transfer by Battistoni. This is just a validation of the discontinuous terms, so this is a pure breakup comparison of numerical and analytical results. So we start from the black line. The line is analytical results, and the dots are numerical results. And as time goes on, due to breakup, our bubbles become smaller and smaller. This is the same thing in the opposite direction. So this is coalescence. Black line is our initial conditions. Black dots are initial numerical conditions. And as time passes on, the bubbles become larger and larger, but there is a smaller number of them. Okay, so let's assume that our bulk fluid model gave us the correct pressures, correct number of bubbles, correct bubble sizes. How can we calculate what is the amount of cavitation erosion? There are two types of models that we can use. The first one is called probabilistic models. The idea here is after each time step, you sample all your faces, you construct a hemisphere around your face, and in this hemisphere, you look for two criteria. This first one is a vapor criterion. Basically, you look if there are bubbles in this hemisphere, and usually the criteria is above 0.5%, 0.1% or something like that. And the next is a damage criteria. You look at whether the conditions in the sphere, if a collapse happens, if that collapse could damage the surface. The damage criteria, two are most popular. The first one is the microjet model by Dular and Gutierrez-Dalgosha, again, focusing on the initial microjet and the damage of it. And the second one is a bubble collapse model, which is based on the pressures for a symmetric bubble collapse. The model is validated on an axisymmetric geometry. Basically, it's a vertical pipe that goes onto a plate, and you would have cavitation around the edges, which would erode a surface 20 to 30 millimeters from the center. This is validated on a well-used K-omega SST turbulence model. It's considered non-dispersed, so everything is prior to this is very well validated. The idea is to just validate the erosion model. So these are the results. Colored is the phase fraction. On the bottom, you have the target plate, let's say, and the red lines here and here is where we expect cavitation erosion to happen. And the black coloring is the amount of the cavitation erosion coefficient. So as we have these structures or cavitation sheets that they come closer to the surface and they erode the bottom plate. Comparing this to experimental results, we can see it's quite a good match. So the red line are experimental results. The blue line is the microjet model, and the green line is the bubble collapse models. So both of them performed well. However, the main issue is you only get a coefficient. The experiment, ideally, you would do an experiment, you would take the plate out, you would weigh the plate, and you could see the mass loss is however many grams, and then you can figure out what is the actual loss. Using these models, probabilistic models, you only get a coefficient of use, not the actual pressures or the mass or the volume of surface that is lost. This brings us to different type of model called called bubble collapse models. The idea here is to actually model the collapse of a bubble near surface and figure out what the pressure is, and then from the pressure on the surface, figure out what will the erosion or the volume or mass loss be. We can do this by using Euler equations in a conservative form with a level set method with a fast sweeping method. The scheme is Mussel-Hancock, and the jump conditions are implemented using a real ghost fluid method. So on the right, you can see what this looks like. This is a helium bubble being hit by a shock wave in air. And these are some numerical results shown here. So it matches quite well, at least qualitatively. And we've come to the last slide, discussion and conclusion. The conclusion is the bulk fluid model seems to work well, especially in the middle of the domain. However, there is a bunch of questions near the wall. There is no universal set of momentum interchange terms. The bubble breakup and coalescence framework are validated, but they again depend on the momentum exchange and bubble induced turbulence. The future work is focused on kind of determining the location of the bubble collapse near the wall by either reconstructing the bubble centers or transforming these bubbles near walls into Lagrangian structures. And cavitation erosion models, the first idea is to expand the probabilistic model to include different hemispheres, the different hemispheres depending on the size of the bubbles that are collapsing. So instead of considering a single set of cells, you would consider a different set of cells for different bubbles of different sizes. And lastly, the individual bubble collapses have been validated qualitatively, but they need to be validated quantitatively and assembled into a bubble collapse library for computation. That's it. Thank you for your attention. My name is Fran Delic. You have my email there. You can find me outside or Hoover me. And thank you to my industrial sponsor, Afton Chemical, for their financial and technical support. Thank you.
For your emails, you have to come.
Yes. Yes. Yes, that is one of the options. Block coupled is excellent because you don't have to answer the question of what you do if the sum, if you solve it sequentially, you will not get a sum of 1. So you would get either 0.9999 or 1.111. And then you need to answer the question, where will I subtract or add the volume fraction to? So if you solve them in a block coupled matrix, it should be bounded from the bottom and from the top. So that's a very neat application of block coupled solutions here. So far. Okay, so I got the first part of the question. Do I consider bubbles colliding? But I didn't get the second part. If you could just repeat that a bit louder. Sure. Yes, that's how we do coalescence. So I am considering that. Again, the main issue with validating all of this, it's quite easy to do a bunch of coefficients and calculate a bunch of data. It's very difficult to validate it quantitatively. So coalescence models are basically the probability of something being of two bubbles hitting each other and the probability of that when the two bubbles hit each other of them merging, and you have models for both of this. So yes, it is being considered. The models themselves are very macroscopic and difficult to validate and of questionable accuracy, at least in my very, very, very short experience. I'm so sorry, I didn't catch that. Could you?
Maybe
Fair enough.
okay.
Yes, of course.
Okay, thank the speaker again.
Thank you.